This is the third and last lecture in our discussion of our module on estimation and hypothesis testing with categorical data. And so in this lecture, we're going to be discussing hypothesis testing using the chi-square test of independence for comparing proportions in two groups. And so the objective of the chi-square test is to determine whether there is a relationship between frequencies or proportions. Remember, those are the same thing. Proportion just is a count of is a percentage of the frequencies. So we're determining whether there's a relationship between frequencies or proportions for two categorical variables. And so the question is, are they dependent, which means there's a relationship between those two variables, or are they independent, which means there's no relationship between those two variables? And so note here that only two-tailed hypotheses can be tested. We're only testing for whether or not there's a relationship. We're not testing for direction on that relationship. So this test is often used to determine whether there's a relationship between exposure and disease status, so say smoking and cancer, or whether there's a relationship between testing a given test and disease status. Say you tested positive for prostate cancer and then actually having the disease. Also, the chi-square distribution, which is another parametric distribution, is used to test hypotheses here. And so the chi-square test is used with contingency tables. And if you'll remember from modules 6 and 7 where we discussed contingency tables, these are tables that show the distribution of one variable in the rows and another variable in the columns and how they intersect. And it's used to study the association between two variables. And so often we're speaking about a two-way contingency tables. And so the rows are referred to with the letter R, columns are referred to with the letter C. So if you want to calculate degrees of freedom for any contingency table, it's the number of rows minus 1 multiplied by the number of columns minus 1. So if we're talking about a 2x2 contingency table, that's 2 minus 1 multiplied by 2 minus 1, and the answer is 1. There's only 1 degree of freedom for a 2x2 contingency table. And so if you can see the example I have below, that's kind of how the rows and columns are denoted in a contingency table. So row 1, column 1 is often referred to with the subscript 1, 1. Row 1, column 2 would be referred to as 1, 2, and then so forth for row 2, column 1, and row 2, column 2. And then it's also important to pay attention to the totals around the ends of the table. So you have on the far right, you have the sum of row 1, the sum of row 2. Then in the bottom, you have the sum of column 1 and the sum of column 2. And then in the bottom far right corner is the total sum, whether it's either of the column or the row. The total sum is actually equal to your sample size. So now let's talk about this complicated chi-square formula for a contingency table. And so when you just look at the formula from the textbook, it does look very complicated and difficult to figure out. And so let me try and help explain this to you. So the first thing I want you to know is in the formula on the upper left, you see this big O and a big E. The O stands for the observed value in a particular cell, and it has a subscript I and J. In this case, the textbook is using I to refer to the row and J to a column. So you remember from the 2x2 contingency table, if we're talking about row 1, column 1, that would be the observation for that particular cell. That is subtracted, so from that OIJ, you subtract EIJ. The E stands for the expected value in that cell, and that's the real trick here in this formula, is calculating the expected values. And the expected value for a given cell is equal to the row total, so the sum of the row multiplied by the column total, the sum of the particular column that cell falls into, and then divided by the total n, which is the sample size that you would find in the bottom, far bottom right-hand totals for the table. So what the formula is doing with the summation sign is it's actually asking you to do for each cell in the table what you see there in the numerator and denominator. So you're basically taking for each cell, you're subtracting the expected value from the observed value and squaring it, and then you're dividing it by the expected value again. You're doing that for each cell in the table, in the 2x2 table, and then you're summing them together, and that's your chi-square statistic. So if it's a 2x2 table, you would be doing that 4 times and summing it together. So for this example table that I've created below that I also showed on the prior slide, you have your row and column totals. If we were looking at O in the subscript 1, 1, that would be row 1, column 1. The observed number there would just be whatever is in that upper left cell. The expected number for row 1, column 1, though, is the sum of row 1 multiplied by the sum of column 1 and then divided by the total sum, which equals to n. And so I've written that out there. And so for the other cells, you would simply apply that exact same formula. And so to get chi-squared, you would do that. You would take the observed for column 1, row 1. You subtract from that the expected for column 1, row 1, using the formula that I'm showing you there. And then you take the square of that, and then you divide that by the expected value for row 1, column 1. And then you do that exact same process for each of the other cells in the table. So you can see there are 4 numerators and denominators there that you're adding together to get the total chi-square statistic. And so in terms of thinking about how to apply this for hypothesis testing, so I've written a recipe here for you that I've also posted in Blackboard. So again, we're comparing the frequencies or proportions in 2 groups. And so the first step is just to set up the null hypothesis. And here the null hypothesis, you just put it in words. There's no difference in the 2 proportions. The alternate hypothesis, you put it in words. There is a difference in the 2 proportions. The next step is to choose your desired value of alpha, and then identify your degrees of freedom, which are equal to the number of rows minus 1 multiplied by the numbers of columns minus 1. Your next step is to identify the critical value for the rejection of the null hypothesis from the chi-square table. So now we're using the chi-square table instead of the z table. And so what you do is you look up the alpha value in the columns of the chi-square table. This is in the appendix in your textbook. And then you look up and the degrees of freedom value in the rows, and then you triangulate using that to get your desired critical value of chi-squared. So if alpha, for instance, is equal to 0.05, and the degrees of freedom are 1, which they would be for a 2x2 table, then the critical value of chi-squared is 3.841. You should note that the chi-square distribution is only positive, and so we're only doing a 2-tailed test. Next, you want to compute the chi-square statistic using that formula that I showed you on the prior slide. So what I'm showing you here, the subscripts refer to the particular cell that you're looking at in the 2x2 table. The first subscript refers to the row that it's in. The second subscript refers to the column. And remember, where the expected value for a particular row, for a particular cell, is equal to, if it's the expected value for row 1, column 1, it would be equal to the row 1 sum multiplied by the column 1 sum divided by the total sum. And then you would do the same for the other expected values. And then lastly, if your computed chi-square statistic is greater than the critical value of chi-square that you looked up in the table, then you reject your null hypothesis of no relationship or independence, and you conclude that the 2 proportions are related, they're dependent. So let's walk through an example here that I hope will make this a little bit more clear. So let's say we have a sample of 8,811 infants, And we're looking at their birth weight and whether they were exposed, lived near some hazardous area, a high hazard area versus a low hazard area. And so our question is there a relationship between high hazard exposure and low birth weight? So you can see our 2x2 table here. The birth weight is in the columns and exposure is in the rows. So looking at any given instance, for instance, those who had low birth weight and were near a high hazard area, you can see that's 181. And then we sum across the rows to get those who were in the high versus low hazard areas, and sum across the columns to get those who were low versus normal birth weight. And then the far right corner, 8,811, that's our total sample size. So we construct our null hypothesis, which is that there's no difference in proportions. Next, we construct our alternate hypothesis, which is that there is a difference in proportions. Say we set our alpha value at 0.05, then we get our degrees of freedom by multiplying the number of rows minus 1, which is 2 minus 1, times the number of columns minus 1, which is 2 minus 1, and our answer is 1. So we have 1 degree of freedom. The critical value for the chi-square statistic at alpha 0.05 with 1 degree of freedom is 3.841. So next, what we want to do is calculate these expected values for each of the cells. And so we already have the observed values because they're in the cells of the table up there with birth weight and the high versus low hazard areas. But the expected values we need to calculate. So the expected value for row 1, column 1 is the row sum, which is 4,449, multiplied by the column sum, which is 307, divided by the total n. And so the expected value is 155 for that upper left cell. And note that the observed value there is 181. To construct the expected value for row 1, column 2, we apply the same process, this time multiplying the row 1 sum by the column 1 sum. We multiply the row 1 sum. Now we're multiplying it by the column 2 sum, which is 8,504. And then again, we divide by the total number in the table, 8,811, to get the expected value of 4,294. And you can see that's different from the expected value of 4,268. And then for the row 2, column 1 expected value, we multiply 4,362, which is the row 2 sum, by the column 1 sum of 307, divided by the total n of 8,811 to get an expected value of 152. And then lastly, for the expected value of row 2, column 2, we multiply the sum of row 2 by the sum of column 2 and divide by the total n to get our expected value there. So now that we have our expected values and our observed values, which were in the table, you can see the chi-square statistic below, where we plug in the observed value minus the expected value squared, and then divided by the expected value. And we add those for each of the 4 cells. And when we add those up, our result is 9.12. And so this chi-square statistic of 9.12 is greater than the critical value that we looked up in the table of 3.84. So the result is that we reject our null hypothesis and conclude that there is a relationship between low birth weight and high hazard exposure.